In this lecture, we are going to see the topic that is related to analysis of proper cantilever beam with the overhang portion. Coming to the question, determine the reaction components for the proper cantilever beam as shown in figure. And here EI is taken as constant throughout the entire beam. This is a figure. This is an ABC beam. You are having BC portion to be overhang, and the total span of this beam is 6 meters, and the point load is acting in between AB, which is of 60 kilonewton. So this beam we are going to analyze. So for this beam, first we are going to find out the number of reactions. At A support, as it is a fixed, you are having 3 reactions. One is horizontal, another is vertical, and next is your moment. And at the B, as it is a roller support, the reaction here is RB, only a vertical reaction. Therefore, the number of reactions are 4, HA, RA, MA, and RB. And here you are having the static equilibrium conditions to be 3, which are sigma fx 0, sigma fy 0, and moment about this xy plane will be 0. Therefore, the degree of static indeterminacy will be 4 minus 3, that is 1. Now you are going to balance the forces. So as in the x direction, there is no any other external horizontal load. Therefore, HA is 0 and sigma Fy is 0. That means RA plus RB is in vertically upward direction, and the 60 kilonewton is vertically downward reaction. Therefore, RA plus RB is equal to 60 kilonewton. Now what you are going to do is to find out this indeterminacy of 1 degree. We are going to assume this entire proper cantilever beam into 2 parts. So first part is something like a simple cantilever beam, which is having only the external load that is acting. That is a point load, which is of 60 kilonewton. Now this load is acting like a eccentric point load. And next second part is same cantilever beam, but at this B support, instead of this prop, we are having a vertical reaction that is upward, which is acting this B support. Therefore, this vertical reaction RB is treated as a redundant force. In the next slide, we are going to calculate the reaction components. So to calculate the reaction components for this entire proper cantilever beam, what we are going to do is at this B support, we are making the net deflection to be 0. So due to this given loading condition, as we are having a central point load acting here for this AB cantilever beam, the deflection we are going to calculate at this B support. Therefore, at this B support, the deflection formula for a point load which is at the centrally placed is 5W L³ by 48 EI. So by substituting all the values here, W as 60, L as 4 meters. So we are considering till only AB portion. This BC is an overhang. After substituting all these values, we got delta B to be 400 by EI, which is vertically downward. And then upward deflection due to this RB reaction is, it is vertically upward. So which is of RB into L³ by 4EI. So this is a vertically upward deflection, that is RB L³ by 3EI. Now what we are going to do is, based upon the consistency condition, the net deflection at this B support will be equal to 0. So that means downward deflection will be equal to upward deflection. By using this, you are going to sort the equation, sort this above equation. Then we are going to get RB as 18.75 kilonewton. As we know, RA plus RB is 60 kilonewton. We got RA as 41.25 kilonewton. So this is how we calculated the reactions. After getting the reactions, then you are going to calculate the moment. So to calculate the moment, what we are going to do is we are going to make at this point moment about B equal to 0. So these are the reactions RB and RA. So moment about B 0. Now this MA is in anticlockwise direction about this B point. So minus MA. and RA is in clockwise. So plus RA into 4 and minus 60 into 2. Therefore, we get MA value as 45 kilonewton meter, which is of positive value. That means you are having this MA is in hogging in nature. After getting this moment, then we are going to draw the shear force diagram by using this reactions and this moment value. So this is a sign convention for a shear force diagram. So when we cut a section at any element, so towards the section, if the shear force is in clockwise direction, then it is a positive shear. If the shear force is in anti-clockwise direction, then it is a negative shear. And when we consider in this CB portion, so as this CB portion, there is no load acting here. Therefore, here the shear force is 0. Then we are going to take a shear force in between BD. So the section we are going to take here. So this is an XX section and which is at a distance of X from the B. Now I'm going to consider the shear force equation from B to D. So the shear force equation is minus RB as this is an anti-clockwise direction. So which is of minus 18.75 kilonewton. So as we are starting from here, I'm taking the B as origin. Therefore, it is a 0. And 0 to 2, the shear force will be same. That is minus 18.75 kilonewton. And then I'm going to take a section in between DA. So this is a section and it is at a distance of X from this B support. Now the shear force equation is minus RB and plus 60. So the limits here are 2 to 4. Therefore, in between D to A, the shear force will be 41.25, which is of positive value. Now we are going to plot the shear force diagram. So this is a beam, and at C, as we don't have any shear force, as well as at the B also the shear force is not there. I mean in CB section the shear force is not there. And now coming from BD section, so at B you are having a shear force of minus 18.75 kilonewton. Similarly at D also it is minus 18.75 kilonewton. So which is of negative value. So I have drawn it in the downward direction. And now coming 2 to 4, at D again you are having it is 41.25 kilonewton, which is positive. Again at A also it is plus 41.25. So this is a positive value. So this is how you are going to draw the final shear force diagram. Since CB there is no load, there is no shear force. And between BD section it is 18.75, which is of negative value. And in AD it is a positive of 41.25 kilonewton. So this is a final shear force diagram. Now coming to the bending moment diagram. So for this entire proper cantilever beam, so these are the reaction components and the moments. So now using this, we are going to now take a sections and all in all these different 3 segments. Coming to this CB, as there is no load, the bending moment here will be 0. Now coming to this BD one, we are going to take a section XX, which is X distance from B. And this is the sign convention we are going to follow. So when we cut a section, when we are having a upward arrow, so heading towards the section, then it is a sagging moment. When the arrows are heading toward downwards towards the section, then it will be a hogging moment. Now when we write a bending moment equation, this is plus RB into X, which is of limit 0 to 2. So when we substitute 0 at B, you are having a bending moment to be 0. And when we substitute 2, you are having a positive value of 37.5 kilonewton meter. Next is when we take a section in between DA. So this is a section XX and which is X distance from B support. Now when we write an equation, this is RB into X minus 60 into this X minus 2. So which are the limits from 2 to 4. Now when we substitute X is equal to 2, we get a positive of 37.25 kilonewton meter. So that is at D. When we substitute 4 meters, then at A you are going to get a negative value of 45 kilonewton meter. So that means you are changing the moment value positive to negative at this D to A section. So now I am equating this bending moment equation to be 0 in a DA section. So when we equate this bending moment to 0, we'll get a point of contrafluxure. So that X value, we got it as some 2.74 meters. Now we are going to draw a bending moment diagram. So this is an ADBC beam. So at C, we are having the bending moment to be 0. At B, you are having the bending moment to be 0. Now at D, we are having a bending moment to be 37.5 kilonewton meter, which is positive. And at A, we are having a negative of 45 kilonewton meter, which is of negative value. So in the D2A, we are changing a sign convention. So this sign convention is changing by equating this bending moment equation to be 0. So that X value here is, sorry, it is not 2.74, it is 2.91 meter. So this is where we are getting the bending moment to be 0. So this is how you are going to draw a bending moment diagram when we are having a overhang for the proper cantilever beam. These are the textbooks and references. Thank you.